Welcome back. We'll continue and we'll start a new unit today. It's intended to be a fairly short unit, and what we're going to do here is solve a boundary value problem for nonlinear elasticity. Okay, so let's get started with that. So we're looking today at a a boundary value problem in nonlinear elasticity. Okay. We've spent quite a bit of time learning about isotropy in the past few segments, and that is the case we're going to take up, simply because it's not necessarily the most general case. It's actually quite a specific case when we say that a material has full rotational symmetry. However, it is because it simplifies our strain energy function considerably. It's one of the easier ones to tackle. All right, so we're going to consider an isotropic material. Okay, and we know very well that what this means is that our strain energy density function can be written ultimately as a function of, how do we denote it? I think psi tilde, function of B, right? Our left Cauchy-Green tensor. Now, something I mentioned in the previous segment is that once you have an isotropic material, one can show that the Kirchhoff stress tau has this form. Okay, and the fact that we have two tensors here which commute, right? We've actually flipped their positions, right, in the third member of this equation. The fact that we can do that comes from properties of isotropy, right? And the property of isotropy applied to our strain energy function psi. Okay, and properly this should be psi hat. Sorry, psi tilde. All right, we have this. From here, one can actually go a step further, right, and consider what this means for the Cauchy stress sigma. Sigma, as you recall, is 1 over j tau. Okay, so that's 1 over j. Remember, j is the determinant of our deformation gradient, times any of these formulas. All right. Now, everything I'm writing here follows from isotropy, right? Now, yet another thing that one can show is that from this form, one can show that sigma, okay, okay. So let me just say this, one can further show that the Cauchy stress sigma has this form. Alpha 0, which is a function of the invariance of B, right, and we know what those are. Multiplying the isotropic function plus alpha 1, also a function of the invariance of B, times B plus alpha 2. All right, I'm sure you're picking up the plot now. All right, one can actually show that this form must hold. All right. Okay, so if we have this, we're going to apply it to the boundary value problem we consider. Okay, now I've taken care to say that we're looking at a boundary value problem. What that means straight away is that we're looking at a steady state case, right, where time dependence is not part of the problem. Okay, so so I'll state that, however, we're looking at a steady state problem. Okay, what that means is that if we look at our PDE, right, which takes on the form right, the material time derivative of the velocity multiplied by the current mass density equals the spatial divergence of sigma plus BF, right, in omega t cross 0, t. Right, that is our PDE. Now, because we're saying that things are at steady state, we can essentially ignore these terms. Okay, this goes to 0. All right, and in fact, what we're going to do is take a further step. Right, we're going to say that, well, we know that all of this can also be written as we know that this can also be written as rho derivative of the material velocity with respect to time, right? We're going to say not only is the partial time derivative of the spatial velocity 0, but we're going to say that this is also 0. Okay, so really we're not looking at time dependence at all here. Okay, so really we are looking at, therefore, a purely boundary value problem. Initial conditions are not relevant, right? So what we have is really we need to just worry about this. Right? In the context of solid mechanics, this type of a problem also is often called a quasi-static problem, right? Okay. Now, we are going to take an inverse approach to the problem that I want to describe to you. Okay. Okay. And what this means is that because of the particular phenomenon I want to be able to describe to you, I am going to start off by first assuming a particular displacement field. All right, so really I'm assuming a solution. I'm saying that, well, this is the solution I want to see. And then I'm going to go back to the equations to see what that implies for boundary conditions. Okay, that's the approach I want to take. So we're going to take an inverse approach, and what this says is that we are going to assume, well, we're not really, I don't like the word assume here. I'm going to say let's consider, okay? Because this is really the case we're considering. let's consider the following displacement field. Okay, we want to consider a displacement field u parameterized by x. Okay, right. Now this displacement field is going to take on the form that you have all seen before, right? This is one of the very first displacement fields we considered that was not rigid. It's what we sometimes call a simple shear field. Okay, we want to write this as we want to write this as gamma times x2, okay, multiplying E1. All right. So what we're saying is that the displacement is all along the E1 direction, okay, and it has that dependence upon the x2 coordinate. Okay, so for our picture of the current and reference configurations, here's what we have, right? We have, I'm going to consider a rectangular block for ease of representation, and I need to make this a little better. I need to get it to align up with the axes I have here. Okay, that's better. So we have E1, E2, E3, okay, right-handed. All right, and okay. All right, so in red we have the reference configuration. I'm now going to draw the current or the deformed configuration, right, arising from the kind of deformation I've specified. Okay, at the risk of overlaying this on the red, okay, that's working. That is what we are trying to represent here. Okay. Okay, I think you can see what I'm trying to represent here. Okay, so that is omega sub t. All right, and of course everything's clear here, right? So omega naught here now in red is our reference configuration. Okay, so it's all very clear. We don't really need to draw very much more. We have the displacement field there and so forth. Okay, so let's go on now and start computing all the tensors that we need from here. Okay, we have f, right? F, remember, is derivative with respect to x of phi, right? And phi, since it's a point-to-point map, is constructed as reference position plus displacement field. Okay, and so when we go through with this, we have isotropic tensor plus derivative with respect to x of that displacement field that we are considering, which has the form gamma x2 multiplying E1. Okay, and by now we are quite expert at carrying out that type of differentiation, and what we get here is gamma E1 tensor E2. Okay, that is F. Right? If you want to see it in matrix notation, just to get a better sense of it, in matrix notation, F would be written as it has ones along the diagonal, okay, and in this position, in the 1, 2 position, it has gamma, Everything else is 0. Okay? All right, excellent. So we have that. Let's go ahead and put down the other tensors. We know that because we're talking of an isotropic material, we need B, right? Which is FF transpose. Right? B equals FF transpose, which is right, that's F. F transpose is just that transpose, so that gives us gamma 1, or the isotropic tensor, plus gamma. The transpose of E1 tensor E2 is E2 tensor E1. Right? And when we carry this out, accounting for the orthonormality of our basis vectors, what you will see is that we get isotropic tensor plus gamma multiplying E1 tensor E2 plus E2 tensor E1. Okay? Sorry for really squeezing it into that corner, but that's really all we need. Okay? And there's one more term that we need to have here, which is the quadratic term. It takes on the form gamma square E1 tensor E1. Okay? And now, to keep things clear, let's also put down matrix notation for B.